So I'm Henri Tervo. I work as a postdoctoral researcher at the Materials and Mechanical Engineering Unit, the University of Oulu in Finland. And today's topic is a collaborative project with the University of Miskolc and with the SSAP. And I'd like to introduce the group with whom I've been working. So Doctors Marcell, Gáspár and Judit Kovacs are my Hungarian colleagues from University of Miskolc. Doctors Antti, Kaijalainen and Vahid, Javaheri are my colleagues from Oulu University. Vahid is actually here in the conference today. And Johannes Sainio is our industrial contact at SSAP, where he is working as a welding engineer. And Professor Jukka Kömi is the head of our unit of Materials and Mechanical Engineering. And this presentation, it was originally intended to be in two separate presentations, but we decided that I will present both of them in a row in the same presentation. So let's go. First, maybe there are some people who don't know where is Oulu and our university. So I would like to tell some basics. We have 8 different faculties. There are more than 13,000 students and almost 4,000 of staff, a lot of alumni. It is one of the biggest universities in Finland. And we are located here in northern Finland. If you like flying, it doesn't take many hours to fly from anywhere from Europe. Currently, we have direct flights to Helsinki and to München, to Germany. Or if you like slow traveling like me, then it takes longer time. Then our unit, Materials and Mechanical Engineering, it is a part of a steel research community called the Center for Advanced Steel Research, abbreviated as CASR. And in CASR, there are other units from our own university, but also from universities, other Finnish universities. And altogether, this community, it's the most important and most important unit in Finland for steel research and steel education. Then we move on to today's topic. So the materials, they are high-strength offshore steels. They are developed for demanding conditions where both high strength and toughness are needed. And typical applications are like offshore oil drilling platforms, wind power mills, or ships, for example. And these base materials, they are engineered to have very good strength and toughness, but the weakest locations are generally the welded joints. And that is because the thermocycles caused by the welding alter the original microstructure, and that way also weakens the mechanical properties. And when welding thick sections, it may require multiple welding passes. And then when welding multiple welding passes, the thermocycles affect not only the base material, but also the earlier welded filler material sections. And there are quite a lot of research about the effect of heat-affected zones on base material, but not so much research about the effect on filler material. So that's why in this study we decided to study that. And shortly about the materials, they were 60 millimeter thick 500 megapascal offshore steels. They were welded by single pass submerged arc welding method, which is generally used with this type of steels. And filler material was ESAB's filler material. And here you can see the chemical composition of both base material and filler material, and also the AC1 and AC3 temperatures calculated by JMAT Pro based on these chemical compositions. And methods. On this single pass weld, we simulated heat affected zones by Liebel, and then we measured impact toughness by instrumented Sharpie V-notch test. Hardness measurements were done also, and then we did microstructural characterization and fractography studies and inclusion scans by FSM. And for inclusion classification, we used our own characterizer tool that was developed by my colleagues at the University of Oulu. And for the thermal cycles that were simulated, we had two different heat affected zones: coarse-grained heat affected zone and intercritical heat affected zone. And the peak temperature here, it was 1350. That means that the steel is fully austenitized in this temperature. While here in intercritical heat affected zone, the peak temperature was 815, which means that it is between AC1 and AC3 temperatures. So it is partly austenitized. And we used three different cooling times, which represent the typical cooling times which are used in welding this type of steels. Then about the impact toughness results. So the original weld impact toughness is here, and you can see that in coarse-grained heat affected zone there are not much variation. It is a bit less, and with the shortest cooling time, there is a lower impact toughness than with the higher cooling time. But the lowest impact toughness was seen in intercritical heat affected zone, and the trend was that it went down when the cooling time was increased. But still, even in this case, what was the lowest impact toughness, it easily exceeds this requirement according to standard, which is 20 joules in at minus 40 degrees. And here we are in more than 100. So still relatively good impact toughness anyway. And in macro scale fractographies, we see mainly that unaffected weld metal, it is very ductile. It is mostly ductile also in other cases, but here in intercritical heat affected zone, there are more brittle sections, but we will see SEM images of this later. And then with this instrumented Sharpie V, in addition to the absorbed energy, we also see other data. We can have a force displacement diagrams, and we can have a fraction of energy that went for initiation of the crack and that went for propagation of the crack. And these graphs, they can be, from this we can read the failure mode, if it's like completely ductile or partly ductile. And for example, here in unaffected weld metal, this looks very ductile, so it is similar to this. While then, for example, here in intercritical heat affected zone, we see some unstable crack propagation here. And then we'll move on to microstructures. This is the original unaffected weld metal. Microstructure consists of acicular ferrite mainly, but there is also grain boundary ferrite and ferrite side plates are also present. And then these images, there is a intercritical heat affected zone and coarse-grained heat affected zone with different cooling times, 5 seconds, 15 seconds, 30 seconds. And what we can see, mainly it is still acicular ferrite. And we can also see, as a reference, we have hardness values here. We can see that in coarse grade heat affected zone with 5-second cooling time, the hardness slightly increased. But in other cases, it is more or less the same, so there is not much variation. And we can also see that when we have this grain powdery ferrite regions here, they are still present after the heat affected zone simulation, like here, for example. And also we can see when we saw earlier the impact toughness results, the lowest impact toughness was in this intercritical heat affected zone with 30-second cooling time. And in this case, we can see that there are this kind of larger ferrite, like quasi-ferrite areas. So it might be that these are connected to the lower impact toughness in this. Okay. Then some examples of fractographies by SEM. So in original, it is mostly ductile, but even if in macro scale it is ductile, there are still also some brittle areas can be spotted. And here is a good example that we have here brittle ductile fracture also here, but between them there is a region of brittle fracture. And this is quite well connected to the microstructure that we had this acicular ferrite mainly, but then we had this grain powdery ferrites. And these grain powdery ferrite areas seem to have this brittle fracture, while in acicular ferrite regions, it is ductile fracture. And also, as in previous image, we saw this quasi-ferrite regions in intercritical heat affected zone with 30-second, and they are likely connected to these cleavage fracture areas, and you can see that also some crack had started from these. Okay, then I'd like to tell something about the inclusion results. They are quite interesting. They are still preliminary results, and we need to do some further scans to confirm, but I am showing this because they look quite interesting. Because here in is it? Oh, it stopped working. Okay, but yeah, I mean this laser doesn't work anymore. Yeah, but yeah. Anyway, you see here coarse-grained heat affected zone, and in these cases we have a lot more small inclusions than in original Weld and in intercritical heat affected zone. We still need to do more scans to be able to say for sure it is real result. It can be also related to small scanned area, and if we happen to have this kind of clusters like we see here, more of them than in other cases, it may have affected the results. But still, it looks interesting. And we have when we see the chemical composition of these inclusions, this example is from the original Weld, and it can be seen that it is like mixed oxide, but on the surfaces there is a manganese sulfide, little manganese and little sulfur. And when we look at the distribution of in all cases, we see that in this coarse-grained heat affected zone where we had much more small inclusions, they have this manganese sulfide particle, and it may be one explanation, because in this coarse-grained heat affected zone, simulation, we go to peak temperature 1350, and in that temperature already manganese sulfide nucleation can happen. And for example, if we have an oxide and there is a manganese sulfide on the surface of it, and if the manganese sulfide part grows, then of course also the inclusion grows. And if initially it was below 1 micron, then after this growth of manganese sulfide, then it exceeds 1 micron, and then we see it here in results, because the 1 micron was the minimum size that we included in the results. Oh, yeah, in the summary already. So regarding toughness, it was seen that the requirements are surpassed in all cases easily. And when we it works again. When we see the impact energy, it was seen that it decreased in heat affected zones compared to the original Weld, and especially in intercritical heat affected zone with longer cooling time. And microstructure was primarily acicular ferrite, but there were grain boundary ferrite and ferrite side plates too. And fracture behavior, regarding that, the brittle fracture was connected to regions where we had grain powdery ferrite. And as you saw, the inclusion results, they were quite interesting. There were a lot of small inclusions in coarse-grained heat affected zones. And I'd like to also tell some about our future considerations. Currently, we are having fracture toughness measurements. We will have results later. And also we are going to characterize the microstructures more accurately with the EPSD. And now we have studied only one type of pillar material, but in the future intention is to make similar studies also using different pillar material. So that's all from me. Thank you. And if you have questions, I can try to respond.